I'd like to talk to you about age of the Earth, and I'll try and do it in a lighter format so you can understand a little bit about my views of radioisotope dating. Grand Canyon, the inside story of the ground beneath our feet. You look around the Earth and you see evidences of the historical operation of process on the Earth. What formed the Earth? How did it form? When did it form? All kinds of questions come to our mind. How did those fossils get buried in there? What's that river doing in the canyon? All kinds of erosional forms and things like that. You might have detected from my previous discussion about Mount St. Helens that I have not always been a creationist. In fact, I was an evolutionist in my way of thinking about the Earth originally. Why did I once believe in an old Earth? I tried to put down the 5 things that convinced me of an old Earth. Laminated sedimentary rocks, things that seem to be deposited very slowly. Fine grain, textures, things like that. Large canyons with small rivers. Grand Canyon being one of the largest canyons I know, and it has a river down in the bottom, Colorado River. Petrified forests, the idea of succession of forests. Coal beds deposited in peat swamps, and radioisotope dating. Those are the primary evidences for why I once believed the Earth was old. Do you want to know what my primary evidence is for why I believe the Earth is young? Those. The same ones, okay? And that is interesting, isn't it? Okay, I investigated the processes and the products that used to convince me the Earth was old, and I started learning more about it, and it started to convince me the Earth was young, and so that's interesting. So laminated sedimentary rocks, I thought they were formed by the seasonal alternations between summer and winters, between wet years and dry years, and the boundary between adjacent thin sedimentary units represented long periods, sometimes nothing happening, long periods of inactivity. I've been reinterpreting that at Mount St. Helens in terms of rapid sedimentary process. I've kind of specialized in rapid granular flow of materials and discovered that the shearing action when grains flow over a surface segregates them by size, by shape, by their density, and creates laminated sedimentary deposits rapidly. And it's interesting to go look at the laminated sedimentary structures in the Earth's crust in terms of what we have seen in the laboratory, in flumes, and also what we've seen at Mount St. Helens, a natural catastrophic process. Large canyon with big rivers used to convince me of long periods of time. And when I first saw the Grand Canyon, I was thinking in terms of long ages and slow process. Did the Colorado River cut Grand Canyon? As I studied that issue, and most geologists have generally gone along with this, it doesn't appear that there's a 70 million year record of erosion of the Colorado River in Grand Canyon. There appears to be some kind of abrupt, almost instantaneous event that positioned the Colorado River through the upwarp plateau in northern Arizona. And it leaves open a young Earth interpretation. And the small river in the big canyon, it doesn't look like it was a little water over a long time. It looks like a lot of water over a little time. And those petrified forests, like at Yellowstone, used to convince me of successive forests. I used to think in terms of each forest level representing, or each level with petrified logs representing an individual forest. And as I explained earlier, the succession of forests, supposedly 27 distinct forests at Yellowstone, was evidence of tens of thousands of years of repeated forest growth, one on another. These forests grew, then soil developed, then another soil formed after a forest was buried, and then a second forest grew, and that whole thing happened repeatedly. And that could require multiplied thousands and thousands of years, the whole succession of strata, perhaps 40 million years in duration. We have seen at Mount St. Helens a miniature laboratory for the study of deposition of petrified forests and the way the logs float in Spirit Lake. 1 million logs landed in Spirit Lake after the eruption due to that giant water wave, and those logs have been floating around in that lake now for 23 years. I've been able to watch how the logs float and how they sink to the bottom of the lake. And one of the amazing things that we've discovered is that the logs in Spirit Lake float in upright position, and then as they sink to the bottom, they can stand on the bottom and get buried in vertical position, having the appearance of being a forest, part of a forest, a tree that grew in place. And so that's very interesting. And as we did the sonar survey there at Mount St. Helens, we discovered something like 20,000 upright objects on the bottom of the lake. And what would Spirit Lake look like if you drained it? It would look like a forest that grew there. But it's not a forest that grew there, it's a transported forest or a replanted forest on the bottom of this lake. And the whole configuration there suggests that there's some other explanation, perhaps, for the petrified forests at Yellowstone. And so that's interesting to see the process. And we looked critically at the Yellowstone petrified forests, and some of the so-called evidences of rooting in place of those petrified stumps, especially the vertical ones, aren't as strong as we thought they were. And the soil zones between the layers doesn't appear to be soils. And some of the tree rings seem to correlate on different levels, suggesting that forests where their root ends buried at different levels grew at the same time, falsifying the petrified forest interpretation. So petrified forests don't appear to be a conclusive argument for great age of strata. And then coal beds deposited in peat swamps. I told the story of the of coal beds, especially Kentucky coal study I've done, and thinking about floating log mat model for the origin of coal. And then seeing Mount St. Helens produce a log mat and all kinds of accumulation of broken plant material on the bottom of the lake, especially a peat layer up to 3 feet thick with sheets of tree bark abundant in the peat, having the appearance, if it was compacted and altered, of some of the coal beds we see in Kentucky and in the eastern United States. So coal beds deposited in peat swamps maybe need to be reinterpreted, and maybe not a swamp at all, but maybe underneath a floating log mat. So a log mat model for the origin of coal could happen rapidly, such as the peat accumulated at Mount St. Helens. And then the final one is radioisotope dating. And that's the one that the RATE project is attempting to address. And that was the one of the 5 that used to convince me the Earth was old. And I'll tell you that story. I'm going to talk about the radioisotope story. I've talked about the first 4, so now we can talk about this last one, radioisotope dating. Just a story. Okay, and it's late, and let me give you this story. It's kind of a lighthearted story, and it'll help you understand the nature of assumptions. They get involved in the way we think about the age of things. One day there were 2 space travelers that came from a distant planet. They came to Earth, and the purpose of these space travelers, of all things, was to understand the average age of a high school student, believe it or not. And they came to 2 different high schools, one here in Indiana, let's say, and one in California. And their purpose was to determine the average age of a high school student using scientific methodology. So our friendly space travelers landed here in Indiana, and what did they do? They measured the heights of high school students. And they measured hundreds of high school students, and they found that the average high school student is 65 inches high. And over the 3 years that they were measuring high school students, they discovered that the average high school student gains 1 inch per year. So how old does the average high school student appear on the basis of their height and their height gain? 65 inches high, and they gain 1 inch a year, would appear to be 65 years old. Well, our friendly space travelers who landed in California, they studied the California students, and they discovered the average high school student weighs 130 pounds, and after measuring hundreds of high school students, they discovered the average high school student gains 2 pounds per year over the 3-year period they measured high school students. So how old does the average high school student appear on the basis of their weight gain? They weigh 130 pounds on the average and they gain 2 pounds per year. How old does the average high school student appear on the basis of their height and their weight gain? Okay, good. You guys are really on to that. Okay, so our friendly space travelers got together here and started thinking about this. The average height is 65 inches. The height gain is 1 inch per year. The average weight gain is 2 pounds, 130 pounds is the average weight. Conclusion, the average high school student is 65 years old. Now, when they were doing this, the parents were there. What did the parents say? The parents gave eyewitness testimony that their students, their sons and daughters, were not 65 years old, but they were just teenagers. The eyewitness testimony conflicted. But our friendly space driver said, we just want the scientific evidence, you know, and so they concluded the average high school student is 65 years old. Okay, question is, what went wrong? What went wrong? Okay, think about it in our story here. Assumed constant rate. They extrapolated the weight and height gain over the life of the student. Teenagers are kind of unusual people, right? You don't want to extrapolate over their interval. Okay, assume zero initial condition. A baby, when it's born, has 0 height and weight. That's not a good assumption, is it? And they disregarded eyewitness testimony. They just wanted the scientific argument. Okay? Some things went wrong there, didn't it? Radioisotopes, similar. Here's some of those assumptions. Dr. Vardaman mentioned some of these. A closed system. We have an hourglass here with grains in the upper chamber and the lower chamber. We haven't removed or added any grains to the hourglass, if you will. The beginning quantities are known. We might assume that all of the grains were in the upper part of the hourglass as we begin, and there were no grains in the bottom of the hourglass, but that might not be the initial condition there. And constant rate of decay, or in the case of the hourglass, constant fall of grains through the apparatus. Those are some of the assumptions, and I think all of the assumptions can be questioned. And so that's what radioisotope work needs to be done. The Uncle Fred story. Okay, here's the Uncle Fred story to help you understand uranium-lead dating a little bit. A gift from your Uncle Fred on your birthday in the year AD 2003. You have a strange uncle, and he gives you a safe deposit box. Inside of there are 16 uranium atoms. Okay? Okay, now, what do you do with that? Uncle Fred gave that to you, and what are you going to do with your 16 uranium atoms? Well, you think about it a while, and they're radioactive, aren't they? Okay, and you just don't put that under your bed. You want to put it in a safe place. You think, where would be the safest place to put your safe deposit box? And after thinking about it, you say, the Federal Reserve Bank in Washington, D.C.? Well, anyway, according to the story, you put your safe deposit box in a safe place that will forever be there for you to observe. According to the theory of radioisotope decay, what will that box look like in the year 4,500,000,2003 AD? What would it look like? According to the theory of radioisotope decay, the present rate of decay of uranium-238 to lead-206, it should have 8 uranium atoms and 8 lead atoms. Okay, you see how that works? Okay, what would it look like in the year 9,000,000,000 2003 AD? you should have half of a half, or 4 uranium atoms, 12 lead atoms. And what would it look like in 13 billion, 500 million, 2003 AD? You should have 2 uranium atoms and 14 lead atoms. You see how that works? Half of a half over that decay period, or that what's called half-life. And so that's the kind of the interesting thing about the principle of radioisotope decay. Now let's say something, you lost track of what year it was that Uncle Fred gave you that gift. Okay, let's say you lost track of your birthday, what birthday Uncle Fred gave you that gift. Could you use his gift to tell time? Answer is yes, you could, couldn't you? So what you would do is, you stashed the gift back in the bank safe deposit box. You could go over there and look in the box and see what is the proportion of uranium to lead and get some idea of age. So you go over to the bank and you see this. You see 8 uranium atoms, 8 lead atoms. What do you suppose? You could calculate the age, 4.5 billion years, 1 half-life of uranium, say. That makes some assumptions that nobody's fiddled with your box, added or removed things, that there's been this constant rate of decay, and that we know what the initial condition was, that we all had uranium atoms to begin with. Okay, you kind of remember vaguely back there what that birthday was like, and you think there was 16 uranium atoms. Okay, well, the Uncle Fred story shows the nature of assumptions as they get involved and how you could use radioisotopes to tell time. Okay, important radioisotope pairs that you use to estimate age: uranium, lead. Uranium is the parent, lead is the daughter. Thorium is radioactive, giving another kind of lead. Potassium changes to argon. Rubidium changes to strontium. Samarium is a rare earth element, is radioactive. It transforms itself to neodymium, another rare earth element. And carbon, some carbon is radioactive. That's carbon-14. It transforms itself back to nitrogen-14. So those are some of the radioisotopes that are useful. Assumptions, again, closed system. Beginning quantities are known, constant rate of decay. All those 3 things have to be stipulated. Some type of closed system assumption, the beginning quantities are known or can be inferred in some way, and we have constant rate of decay. The rate project and the rate researchers have been doing some studies, and that's here's the committee, the rate committee. 1, 2, 3, 4, 5, 6, 7. Okay, and we have the rate research project. I'd like to tell you a little bit about what some of the things that the rate project has done. Radioisotopes in the age of the Earth. We're testing the assumptions of radioisotope dating. We're developing alternate models for interpreting radioisotope dates and data. And we're writing technical reports. That's what's been going on. Research group goals. Current rate projects, it's like a giant jigsaw puzzle. Kind of putting together pieces. How are we going to put together the radioisotope data in some type of coherent way? There's discussions of theoretical models for accelerated alpha and beta decay. Dr. Eugene Chaffin's work. Search for dating concordance and discordance. That's what I'm working on. I'm searching or testing rocks for concordance and discordance of the dating techniques. Search for decay traces of short half-life isotopes in rocks, especially that radio halo work of Dr. Andrew Snelling. Measurement of helium diffusion in minerals. Dr. Russell Humphreys, primary investigator there. Measurement of helium and argon content in minerals, and that's being done also by rate researchers, and in measuring C14 in coals, and maybe even in diamond. It'd be fun to measure some high carbon content materials to see if there's any measurable C14 in those. Those are things that are going on, and you'll probably see those in the final report. Some interesting results: very high abundances of radioisotope decay products occur in some minerals. especially those zircons. Remember that, that Dr. Vardaman talked about. Different dating methods often give discordant dates for the same rock or mineral. And I've been working on that, and it looks like it's usually give discordant dates for the same rock or mineral. I'll give you some information on that here and before I finish. And then radiogenic gases, argon and helium, occur in larger quantities in minerals than conventional dating methods assume. We're finding that argon associated with the zircons especially, or the helium with the zircon, and argon associated with potassium. Helium diffuses rapidly from minerals. How can helium and decay products be so strongly associated with these minerals? And then halos of short half-life elements occur in many common rocks, suggesting rapid crystallization of these rocks in some way, either by fiat creation or by rapid igneous process. So the halos are something that's very interesting. Let me tell you about my work here. Okay, mineral isochron method applied as a test to the assumptions of radioisotope dating. The ultimate date that a geologist would feel confident in is what's called an isochron date, or an isochron method. You date or measure the isotope ratios of multiple rocks in a cogenetic unit, or you measure different minerals in a single rock, and you plot those on a graph and use the slope of the line to indicate what's called an isochron, and then estimate the age. That's the ultimate dating method. And the age of the Earth is currently 4.54 plus or minus 0.02 billion years, according to the lead-lead isochron, which is a sloping line formed from meteorites, of all things, the lead content of meteorites. And it's not the age of the Earth is really done on meteorites, the current estimates. But the isochron method is the favorite method for dating things. So I've been involved with my own isochron dating. Dates on Bass Rapids Diabase Sill in Grand Canyon. There you see the Grand Canyon block diagram. And one of the units down in the bottom of the Grand Canyon here is the Diabase Sill, this Diabase intrusive in the Hakatai Shale. And I've been able to collect that with Dr. Andrew Snelling. We have sampled that, and together we are measuring the isotope ratios of various rocks, about 11 different rocks, and minerals, up to 7 minerals per rock in the Diabase Sill, Bass Rapids Diabase Sill. It's intruded between strata, so it has to be younger than the strata that it's contained in. It's rapidly emplaced because it shows evidence of forceful injection, and because it couldn't intrude itself slowly, it would segregate into different mineral phases. It's very homogeneous material, and because it's very homogeneous material, it lends itself to the isochron dating assumptions, and it's ideal for whole rock and mineral isochron dating. It's has strong enough evidence, I think, to convince any creationist that it was once in a homogeneous or thoroughly mixed isotopic state. And so the different isotope ratios that may exist in it now need to be interpreted, I think, even whether evolutionist or creationist, in terms of the idea of a homogeneous, thoroughly mixed condition. The dates on the Bass Diabase Sill and Grand Canyon are contradictory, and I had or discordant, and I'd found these in other materials that I've dated. Here's the Bass Diabase Sill. The potassium argon isochron, a whole rock isochron, gave an age of 0.84 billion years. The rubidium strontium isochron, which is the currently accepted age among the establishment geologists for the Bass Diabase Sill, is 1.06 billion years, with a rather small error bar. And so that has been suggested to be the age. Originally, when the first dates were published, potassium argon dates were there about 800 million years. And that was okay because it sat underneath the Tapete sandstone, and so it gave a Precambrian date. And so the evolutionary establishment originally could live with an age that way. When the first isochron, rubidium strontium isochron, was published 1.06 billion years, that was immediately accepted, and the potassium argon was rejected. I've dated hole rocks from the sill. 11 hole rocks form a really nice lead-lead isochron, suggesting an age of 1.2 billion years. The error bars seem to be discordant with the 1.06 billion year. And then the Sumerian neodymium method gives about just a little shy of 1.4 billion years. And what is interesting is that the 4 dating methods should give the same age, exactly the same age. Within the error bars, they should all overlap. And what's happened is they haven't. And I've done other isochron dates and isochron plots, and similar orders found. What is the true age of the Bass diabase sill? Is it 0.84 billion years? Plus or minus maybe 150 million years? Is it 1.06 billion years, plus or minus about 50 million years? Clearly discordant with that one over there. Okay, is it 1.2 billion years? A is 0.84, B 1.06, C 1.2 billion years. That's the lead-lead isochron. Or D, 1.4 billion years, the Sumerian neodymium isochron, again with a little more than 100 million year error bars. Or E, what would E be? None of the above. Okay. Now here's what I could argue. I can argue none of the above. None of the above. There we go. Could that be the answer to this question? What is the true age of the diabase sill at Bass Rapids and in Grand Canyon? Now, I plotted this. You want to see error bars and some of the technical data. It looks like the potassium argon dates, those are 2 sigma error bars, so it's 95% chance it's within that error range. Here's that 800 million year age. The rubidium strontium is tightly constrained, somewhere around 1.05 billion years. And the lead is, we're currently refining the error bars on this, but it's somewhere around a little more than 1.2 billion years. And the Sumerian neodymium is up there close to almost 1.4 billion years. The error bars of Sumerian neodymium don't overlap the rubidium strontium, and so there seems to be discordant dates. So I haven't hit a home run, but I'm on first base. I can argue none of the above, can't I? Now here's what I could do. I can propose a model that could explain how to make these concordant. We could have alpha decay accelerated more than beta decay. Do you see what I have here? And I've plotted half-life. And it could be that the alpha decay has been accelerated more than beta decay, and that the higher the half-life, the higher the rate of acceleration of radioisotope decay. And the beta decay the same way. The higher the half-life, the higher the radioisotope accelerated decay. So that's kind of what I'm thinking. And I'm trying to explain why the dates don't agree. And in other rocks, I've seen the same phenomena. The beta decay ages are less than the alpha decay ages, and they seem to be in order of their half-life. And so that is really interesting. And so we're actually going to do more mineral isochron and whole rock isochron on this diabase. The error bars are 2 sigma, so anybody dealing with this data would have to say it's evidence of discordance. Now, we might talk about, is there a physical process that can reset or alter these isochrons in the different mineral phases from their homogeneous condition, we suppose? I don't think it will let the storytelling begin, but this is not a dream come true for an evolutionist model for the concordance of Grand Canyon dates. I dated the lava dome at Mount St. Helens one day. Well, I was walking up in the crater, and I collected from the lava dome a sample of the dacite lava dome that was extruded 11 years before, and I took it back and I processed the mineral phases from it. An 11-year-old lava sample was dated by potassium argon method. I dated the whole rock and I dated the mineral phases. The whole rock age was 350,000 plus or minus 50,000 years. The mineral ages, individual minerals were separated out there. I dated those by the conventional potassium argon method, gave ages up to 2.8 million years for an 11-year-old rock. By the way, I didn't fill out on the isotope form suspected age when I sent them in. They were blind. They didn't know what I was sending them. And a 2.8 million year orthopyroxene minerals inside the lava dome. It looks like those minerals and the whole rock have in it a large amount of argon. The initial assumption of the argon method is there were no argon-40 originally in the lava when it crystallized 11 years ago on the lava dome. That's the problem. And obviously it's an error. And if you believe the potassium argon dating methods can be applied widely to Grand Canyon rocks or anywhere without critical evaluation, I've got a bridge I want to sell you, because a lot of potassium argon dates are being thrown out. Many of the laboratories that are doing potassium argon dates have quit. They're just not doing them anymore. And so this method is being largely ignored and explained away. Lava dome dates. Helium in biotite and zircon. The helium in those zircon crystals seems to be there, a large part of it. The biotite crystal has a small mineral inclusion, zirconium silicate or zircon in it, and inside there is thorium and uranium, and the radioisotope transmutation creates helium. Here's a zircon crystal, and they're very beautiful crystals. They're very high temperature minerals, so they don't easily melt, and the lattice structure retains a lot of helium. And remember that what Dr. Vardaman said, helium leaks out very easily. It's lightweight, it's fast moving and slippery, and over billions of years, there should be a very low quantity of helium in the zircons. It should be in the atmosphere. Instead, we find very little helium in the atmosphere, and we think a large part of the crust of the Earth has lots of helium stored in it. It wiggles through crystals and it leaks through cracks in the crystals, but it seems to still be there. In other words, its rate of diffusion is high, and yet it's still there. That could be an argument for young zircons or accelerated radioisotope decay. Well, why did I once believe in an old Earth? Okay, and that's interesting, isn't it? Now, those are the reasons I believe in a young Earth. I think radioisotope dating can be interpreted in a young Earth context, along with those other things. A lesson from radioisotope dating. Did I learn this? This is what I learned. I think this is the story. Data are interpreted two different ways. Like I once had an evolutionary interpretation, now I have a creationist interpretation of the data. Bias A goes through the data to interpretation A. Bias B goes through the same data to a different interpretation. So we learn that our presuppositions and what we suppose about things get involved with our ideas of the age of things. A young Earth interpretation is being generated for radioisotope abundances. That's what the RATE project's doing. Okay, well I've essentially finished my lecture, and well ahead of time, because I think we've had a significant day. If you want to talk to me about this lecture, I'll stick around after the lecture, But you have a good evening, and I'm going to turn it back to the convener, sir.